gentlemen, Madam Chairperson, good afternoon. I'm here to talk about the disposal of geothermal gases. Atmospheric disposal of geothermal gases is a subject that has been getting more and more attention in recent years. The reason is that when geothermal production increased in the near habitated areas, an increase in H2S concentration was observed in the areas. So the quality of the air around the power plants really decreased. And this has been affecting the air quality around the power plants of Reykjavik Energy. In this presentation, I will be talking about where the geothermal gases come from, what is their concentration, how much gas are we emitting, and I will also focus a lot on the projects that we are working on to lower the gas emission from the power plants. Emission of geothermal gases has been an inevitable part of high temperature geothermal utilization. The major gases the major gases are listed there. It's CO2, H2S, it's hydrogen, it's nitrogen, and in some cases ammonia. These are the gases that are dissolved in the geothermal fluid. Some of the gases are environmentally important. They can be greenhouse gases like CO2 and methane. They can be corrosive, as hydrogen sulfide is. They can be toxic, hydrogen sulfide again. They can be flammable, like hydrogen. And another important environmental factor with these gases is the bad smell. These are really, humans are particularly sensitive to the smell of hydrogen sulfide because it is our defense tool to prevent us from eating rotten food. So we have developed a strong sense for H2S. This is the characteristic geothermal smell that we can smell, and some people, even in Iceland, they have developed a taste for it. They like the geothermal smell, but in general, this is not the case. The concentration of the gases in the geothermal fluid depends on, for example, temperature. Many of the gases are so-called reactive elements. They react they equilibrate in the geothermal system. And this equilibrium is controlled by temperature. Some, for example, then a hot geothermal system, they contain higher concentration of the gases that equilibrate with temperature. Composition of the fluid plays a big role in the concentration of the gases. For example, if you have dilute geothermal fluids like we have in Reykjavik Energy in our production fields, you can have high concentration of H2S and H2. Whereas if you have saline geothermal fluids like they have in Reykjanes and in Svartsengi, you have lower concentration of H2 and H2S. This has to do with the composition of the fluid, the salinity. And also what plays a big role in the concentration, it is the geological settings of the geothermal reservoir. It depends on if the geothermal area is in a rift zone or if it is in a subduction zone. That plays a major role in this. The origin of the gases, they can be either magmatic, they can be meteoric, they are just gases that were dissolved in the rain that precipitated onto the surface, and then this rain seeped into the ground and became geothermal fluid. This is an example of this is nitrogen. The magmatic gases are primarily CO2, and the gases that are coming from water-rock reaction are H2S and hydrogen. Now, geothermal gases are not all bad. We use, for example, hydrogen sulfide to protect our distribution system from corrosion. There needs to be, because hydrogen sulfide reacts with black steel to form a thin layer of iron sulfide on the pipes. And this layer protects the pipe from corrosion. So there needs to be a certain amount of H2S in the geothermal water that we are distributing within Reykjavik. This is why we have this smell of the hot water. Some people go as far as saying that this is the thin layer that keeps the geothermal industry together. If it wasn't, it would all corrode away. And for example, we monitor the H2S concentration in our system, and if it's too low, actions need to be taken. So there is also a use of the geothermal gases. Now, for gas emission from our power plants, Hellisheiði and Nesjavellir power plants, which are located in the Hengill Central volcano, some 20 to 25 kilometers from Reykjavik. Nesjavellir was commissioned in 1990 and Hellisheiði in 2006. The installed capacity is shown there. It's more than 400 megawatts power and more than 504. It's 290 thermal in Nesjavellir and 133 thermal in Hellisheiði. So it's a quite large power plants. The reservoir temperature in the geothermal areas is between 250 and 300 degrees. So these would be considered fairly hot geothermal areas. The mean temperature, usually the temperature from the production area is around 280. So it's quite hot. That means that the gases that are being controlled, the concentration is being controlled by temperature. The concentration of those gases is quite high. The gases are dissolved in the geothermal fluid at depth, and they are concentrated in the steam. When we bring it to the surface and separate the steam and the water, approximately 95% of the gases that go into the steam, the rest goes with the water and is re-injected back into the geothermal system. And the concentration of the gases is around 0.4% in the steam, which is considered to be quite low. Then the steam passes through the turbines, and after the turbines it condenses, and from the condensers the gases are pumped to atmosphere using vacuum pumps. And at present they are being released in both power plants, Nesjavellir and Hellisheiði. They are being released on top of the cooling towers. This is to provide better distribution of the gases. In the first phase of Hellisheiði power plant, and also in Nesjavellir, this was the case in the beginning, the gases were emitted at the top of the power plant itself through a pipe, through an exhaust pipe, and that in some cases would create high concentration of H2S, of geothermal gases, around the power plant. But that has been changed, and we have now a much better distribution of the gases than we had before. Now, what is the composition and how much are we emitting? The pie charts that there is the composition of the gases that we are emitting both from Hellisheiði and Nesjavellir, and the charts to the right are the amount of emission. The gases at Hellisheiði and Nesjavellir are characterized by low concentrations of CO2. This is just a field phenomenon. We have a low concentration of CO2 in the field, so therefore the gases the CO2 is quite low. You see the H2S concentration in Nesjavellir is higher than in Hellisheiði. But the main problem that Reykjavik Energy has been having with the gas, it comes from Hellisheiði. So the gases from Nesjavellir, they are not affecting the people in nearby communities. The gas emission has been increasing with time, and this is primarily due to the fact that we have been increasing the power production. This is just an installment of new turbines. That means that more steam is going through the power plant, and therefore more gas is emitted. And the total emission last year was 62,000 tons of CO2 and 28,000 tons of H2S. That is quite a lot, but in terms of CO2, this is only 5 to 6% of CO2 emission than from fossil fuel burning power plants of comparable size. This is an important thing to remember. The H2S from the power plant, this is a picture showing a theoretical calculated distribution of the H2S coming from the power plants. These are not always very accurate, but they give us the picture that the area that is affected by the power plant is quite large. And this has been, of course, confirmed by direct measurement of H2S in Reykjavik. The highest concentration measured is around 400 micrograms per cubic meter of air. And this was in 2009. Humans, they start to smell hydrogen sulfide at 7 micrograms per cubic meter. So 400 is quite a strong smell. So actions need to be taken to lower the gas emission from the power plants. Because of this higher H2S concentration in the air in Reykjavik and in Hveragerði, a new regulation has been implemented. It becomes valid in 2014. That is puts strict rules on the amount of H2S in atmosphere. These guidelines, they are stricter than the WHO guidelines, the World Health Organization guidelines, and they really put high demand on the geothermal industry to reduce the emission of H2S. Here is a graph of the H2S concentration in Reykjavik this year, and here is the here is the limit. We cannot go, after 2014, we cannot go above this limit. And you can see that once this year we have gone above the limit. So, the next few slides I will be focusing on describing the actions and the projects that we are taking to lower the gas emission from the power plants. Work started in 1990 or 1989 when Reykjavik was being built, about exploring our options on solutions on how to reduce the gas emissions. So this has been going on for a long time, but it was after the commissioning of Hellisheiði in 2008 that we really put more effort in finding solutions to lower the gas emission. And the method that we are focusing on is to take the gases, dissolve them back into the effluent waters, that is the separated brine and the condensate, from the power plant. We dissolve them in the liquid and re-inject them back into the ground. So we are taking the gases on the same form as they came out of the ground, dissolve them in water and put them back. And the projects that we have been working on, we have been having a pilot scale gas separation station. We have a project called Sulfix, which is re-injection of H2S back into the geothermal system. And then there's a project called Carbfix, which is the re-injection of CO2 into basaltic formation. Gas separation station, I will not go in detail through that, but the geothermal gases, they have different solubility in water, so you need to get rid of the gases that don't dissolve in water before you take the gases, the remaining gases, and dissolve them and re-inject them. So the gas separation station was built around separating the gases. And the initial plan was to separate the gases into 3 streams. One was H2S, one was CO2, and the non-soluble gases, which are hydrogen, nitrogen, methane, and argon. But operating the gas separation station has been very problematic, and the process that was supposed to separate H2S from CO2, which was distillation, we have abandoned that, and right now we are just cleaning out the gases that are not soluble and so we end up with a gas mixture that we can use and dissolve in water. So Carbfix and Sulfix, these two are experimental projects that aim at developing and testing necessary techniques to dissolve the gases, as I was explaining, and re-injecting them back into the subsurface. And they also aim at increasing understanding of the fate of the CO2 and H2S injected, and we also are, the setup of the projects, it uses natural processes to sequester the geothermal gases. I will go explain that a little bit better later, but here is an overview of the Sulfix project. But basically what we were doing, we were taking the gas mixture, which was 65% CO2, 35% H2S and some hydrogen. We were dissolving that in the geothermal brine and then re-injecting it back into the geothermal reservoir where it came from. And we did that. We have been experimenting with that. Last year we injected something like 100 tons of gas. We are carrying out geochemical monitoring of the area where we inject to try to get more information about the fate of about what happens to the H2S, and that is still in progress. But the important part here is that the injection of the gases did not clog the injection well. The Carbfix project is a similar project. We have been, there we are dissolving the CO2 and the H2S in a more concentrated manner. We have higher pressure. We dissolve a lot of gas into a small amount of water, then we inject that back into the ground. An extensive monitoring, geochemical flux monitoring and so on is carried out on the injection site, which is designed to tell us more about what happens to the gases once we inject them. On this slide, I will show you what happens to the gases. Here, what happens is that the gas-loaded water, they react with the basaltic rock. They get the necessary element from the rock into the water to form minerals. The CO2 needs magnesium and calcium to form carbonates. And this is what happens in the ground. This is what we predict happens. Theoretical modeling also predicts this to happen. And the same for H2S. It gets the necessary elements from the rock, and then it precipitates as metal sulfides in the geothermal system. We know that this has a tendency to happen because the concentration of the fluid that we are injecting is far above the equilibrium concentration of the H2S in the reservoir. So the excess H2S, the amount of H2S that is above the equilibrium line, precipitates and form minerals, and will be stored in the ground for a very long time. So why do we aim for this method? Why are we not using conventional method of H2S abatement, which involves oxidation of the H2S to form either sulfuric acid or native sulfur? The reason for that we are focusing on the solubility method is that we consider that we are simply moving the problem. If you take the H2S and form a lot of sulfur, you end up with a lot of sulfur, a pile of sulfur in Hellisheiði that needs to be transported to somewhere, and there is no market for sulfur in Iceland, so we would have to eventually dispose of it in another manner, in a pit or something like that. And for us, that is a worse option than re-injecting it. So this is why we are focusing on that. And this is a slide that I will go through very briefly. It just describes the next step that we are doing. We have been carrying out the experimental injections. They look good so far. So this has given us confidence to move on to the next step and start injecting the gases on a larger scale. This will be carried out in 2014, and then we will evaluate how that is going, and then continue make additional steps until we have re-injected enough CO2 or enough H2S to meet the demands of this new regulation about air quality in Reykjavik. But we will also leave open possibilities to explore other options if this solubility method does not work. So, to summarize, the emission is inevitable. Right now, we emit quite a lot of gas. New regulations puts high demands on the geothermal industry to do something about it. We have been carrying out experimental injection. The result looks good, and in 2014 we will start to inject the gases on a larger scale. So, and hopefully that will increase the public acceptance of the power plants in Hellisheiði. Thank you.